Question is, a hydrogen atom in its ground state is irradiated by light of wavelength 970 angstrom, taking Hc by E equal to 1.237 into 10 power minus 6 electron volt meter, and the ground state energy of hydrogen atom as minus 13.6 electron volt. The number of the lines present in the emission spectrum is. Hence we can see here the initial energy of here light of that of photon will be equal to our Hc divided by, we can say, as lambda. Now Hc value we can say here comes out to be our 12,400 in electron volt angstrom divided by, we have here as 970 in angstrom. So this here on simplification comes out nearby to our 12.6, we can say here something 12.69, which is approximately 12.7, we can say, in electron volt. Now in the question it says this ground state here our electron having energy as minus 13.6 absorbs this energy and gets excited to a higher excitation level. So by energy conservation principle we can see here energy in the ground state plus energy of the photon incident upon it will be equal to, we can say, energy in the NH state. So here energy in the ground state here is minus 13.6, energy here of the photon is 12.7, and energy in the NH state will be minus 13.6, we can say, as Z square by N square. For hydrogen Z will be 1, so divided by, we can say here as N square. Now we can say here this comes out to be our N square as 16, which implies that value of N here comes out to be our 4. So N comes out to be 4, so we can say here the total number of lines present in the emission spectrum will be, our answer is equal to, we can say, as Nc2, or simply N into N minus 1 by 2. That is, when here excited to 4th energy level, the total number of emission line will be 4 into 4 minus 1 by 2, that is 4 into 3 by 2. So this comes as 12 by 2, which is equal to 6. Hence we can say here total number of lines emitted here in de-excitation will be equal to 6. So we can say 6 is the answer. So 6 is our answer. Hence 6 is the final answer.
Hello students, today our question is, consider a hydrogen atom in the electron in the nth orbital and in an electromagnetic radiation of wavelength 90 nanometer is used to ionize the atom. If the kinetic energy of the ejected electron is 10.4 electron volt, then find the value of N. We have given here Hc is 1242 electron volt Newton nanometer here, not Newton, nanometer. So the solution of this question is, we have the wavelength is, that is lambda is 90 nanometer, and we have the energy is given to us 10.4 electron volt, and we have the energy formula is Hc divided by lambda. So we have the Hc value is 1242 electron volt, and this is nanometer, and this is 90 nanometer. So this and this will cancel out. So this is given to us, this is equals to 13.8 electron volt, and we have given here the kinetic energy of the ejection is 10.4. So we can write here, this is 13.8 minus 13.6 divided by N square. So this is equals to energy of ejected electron, that is 10.4 electron volt. So from this we get N square is 4, and if we apply root on both sides, so root N square will cancel out, and this is under root 4, that is 2 here, and this is the answer for this question. Thank you.
Well, hello students. Now we're going to see this question. The question says that the wavelength belonging to Balmer series lying in the range for 450 nanometer to 750 nanometer were used to eject photoelectrons from a metal surface, okay, whose work function is given as 2 electron volts. Find the maximum kinetic energy of the emitted photoelectron. So basically it's telling that in the wavelengths belonging to Balmer series fall on the metal surface. Let's suppose this was the metal surface and the basically the light is incident on it, okay, like this. So basically if the light is incident on it, there will be emission of electrons, okay, with kinetic energy. So basically over here it's asking that what is the minimum means maximum kinetic energy. So if you see energy, okay, energy incident is equal to hc upon lambda. So if you see properly, then energy is inversely proportional to lambda, okay. That means what? Lower the lambda, higher will be the energy, okay. That means what? We have to take a least lambda to find out the highest energy. That means what? We have to take the lambda minimum, okay. So basically if we see over here, energy incident, okay, incident energy, okay, incident energy will be equal to hc upon lambda, okay. Hc is given as what? 1242 electron volt per nanometer, and in lambda is given as 450 nanometer. If you see over here in the question itself, it's given, okay, and this was given to us, okay. So that's why we are going to use that value also. So this will come out to be what? This will come out to be 2.76 electron volt. Got it? So basically now what we have to do? Now we have to calculate the sum. So we know that maximum kinetic energy maximum will be equal to what? Energy, okay, energy incident minus work function, okay. So this is basically incident energy max, okay. Over here we have to write, okay, one thing, that is this is maximum energy. For this we have to take lambda minimum, okay. So now what we have to do? Now we have to find the kinetic energy. So this is given by what? Energy incident minus the work function. So kinetic energy max will be equal to what? This will be equal to the energy incident, which is 2.76, okay, 2.76 minus work function, which is 2 electron volt, okay. So you can see over here it's given in the question itself. So this will come out to be what? This will come out to be 0.76 electron volt, okay, 0.76 electron volt. Got it? So basically this is the answer, okay. Thank you. So our answer will be what? Our answer will be 0.76 electron volt. Got it? Thank you.
Hello students. Our question gives that a hydrogen-like atom with atomic number Z is in an excited state of quantum number 2n. It can emit a maximum energy of photon of 204 electron volt. If it makes a transition of quantum state n, a photon of energy is 40.8 electron volt is emitted. Find n, Z and ground state energy in electron volt of this atom. Also calculate the minimum energy in electron volt that can be emitted by this atom during the excitation. Ground state of hydrogen atom is minus 13.6 electron volt. Okay, so we can analyze first of all what is given. We are given a hydrogen-like atom with atomic number Z. It is an excited state, quantum number 2n. So the maximum energy given by that particle is 204. So maximum energy means the transition is from, to give maximum energy, the transition should be from E, 2n is the quantum number, E minus to the ground state, that is E1 is equal to 204 electron volt. This is a maximum energy. Okay, and we are familiar with the energy equation, that is En is equal to E1 divided by n square. So E2n means E1 divided by 2n whole square, that is 4n square minus E1 equal to 204 electron volt, or we can write E1 into 1 minus 4n square minus 1 is equal to 204 electron volt. Let it be equation number 1. Okay, then what is the second case given? If it makes a transition to the quantum state n, energy is 40.8 electron volt. So here the next transition is set from E 2n2, which is a state En, that is E2n minus En, and that energy is given by 40.8 electron volt. Okay, we can also substitute the value, that is E1 divided by 4n square minus E1 divided by n square is equal to 40.8 electron volt. We can take E1 divided by n square as a common, and 1 by 4 minus 1 equal to 40.8 electron volt, or minus 3E1 divided by 4n square is equal to 40.8 electron volt. This be equation 2. Okay, we can divide equation 1 by 2. That is 1 divided by 2, which gives, what is 1 divided by q? That is E1 get cancelled, and 1 by 4n square minus 1 divided by minus 3 by 4n square equal to 204 divided by 40.8. Okay, or we can say, we can take the, okay, we can cross multiply with this, or we can take here in the numerator, we can rearrange with this. So it is 1 minus 1 by 4n square divided by, so this negative sign get cancelled, 3 divided by 4n square is equal to 5. 204 divided by 40.8 is 5. We can cross multiply. So 1 minus 1 by 4n square equal to, on cross multiplying we get 5 into 3 divided by 4n square, or 1 equal to 15 by 4n square plus 1 divided by 4n square, which is equal to 16 by 4n square, which is equal to 4 by n square. So we get 1 is equal to 4 by n square. So n square is equal to 4. So what is n? N is equal to 2. So we get the orbit n is equal to 2. Okay, next our aim is to find Z. Okay, to find Z, we know the value as, we can take equation number 2. What is equation number 2? Minus 3E1 is equal to 4n square equal to 40.8 electron volt. Okay, and we know that E1 is equal to minus 13.6 Z square. Okay, this is the energy of the ground state orbit. So we can equate this thing and substitute n here. Substituting n, we get minus 3E1 divided by 4 into 4 is equal to 40.8 electron volt. On cross multiplying, we get E1 is equal to minus 217.6 electron volt. We can compare both this equation. So minus 13.6 Z square equal to minus 217.6 electron volt. So negative sign get cancelled, and Z square on solving we get it is 16. So Z is equal to 4. So atomic number is equal to 4. Our second answer is 4. Our orbit number is 2. What is our next question to find? It is asked to find the minimum energy that can emit by this atom during the d excitation. So minimum energy means the final orbit to very next near orbit, that is E minimum is equal to, from the final orbit, that is E2n minus the next orbit means E2n minus 1. What is 2 here? What is n here? N is equal to 2. So we get E2 into 2, 4 minus, it is E3, or we get E1 by 16 minus E1 by 9, or it is E1 into 1 by 16 minus 1 by 9. That is, what is E1? E1 is minus 217.6 into minus 7 divided by 16 into 9, which is equal to 10.58 electron volt. So this is a minimum energy. Okay, so these are the three factors or three answers we are asked to find in this question. Okay.